Alright guys, let's pick up with our trig unit here. We kind of talked about reference angles and how they're going to be used, and we'll definitely see a lot of that in the problems today. So let's start out with just a little warm-up first off. Let's say the terminal side of an angle in standard position. So again, we know standard position always will start on the x-axis, so that's going to be the initial side of the angle. They're telling us the terminal side goes through the point -3, 4. Okay, so there's a point there, and then there's our terminal side. So our actual angle is that guy right there, okay, somewhere between 90 and 180 degrees because we're in quadrant 2. And now we are asked to find the sine, cosine, and tangent of that angle. Okay, so the thing is we don't know the exact angle measure, okay, we don't really need it yet, or for this problem. I mean, we could probably find it after doing a little work. But the idea is, again, we're going to use what's called a reference angle, okay, and we're going to make the reference triangle, and the idea there is take the terminal side of the angle, which is this guy right here, and you always want to get back to the x-axis. So if you are in quadrants 2 or 3, remember quadrants, that's 2, and this is 3 down here. If you're in one of those two quadrants, the quickest way back to the x-axis is over on the left side here. Okay, so our right triangle, there's the point. Our right triangle is actually right here. Okay, and this angle from here, from the x-axis, up here, that is the reference angle theta prime, and we're going to use that to get the trig values, the trig ratios, the sine, cosine, and tangent of the blue angle theta. Okay, so the trick is just think about it as a right triangle. Okay, we should know the side lengths because we know the x and y coordinates. Okay, you can kind of see this bottom part here. The length of that side is, even though it's going -3 as a length, it's still just length of 3. The vertical side over here is the y coordinate. And then we can use Pythagorean theorem. This was in the same as the example the other day. You could do 3 squared plus 4 squared equals, and you'll solve for the hypotenuse ends up being 5. And if you want to verify that, feel free to do that. Now here's the thing. Here's what's going to be a little bit different. Well, first off, the sine of the angle is always opposite over hypotenuse. Okay, and the good news is the opposite side, when you set things up in this method, the opposite side is always going to be the y coordinate. Okay, so the y value is 4, the hypotenuse was 5. Okay, that's opposite over hypotenuse. Now the cosine, of course, is always adjacent over hypotenuse, right? So the adjacent side, in this case, or in any case, it will always be the x-axis, right? If your angle's right here, the way we draw those reference triangles from the other day, the adjacent side will always be the x. Now keep in mind, its length is 3, but since it's to the left, it's actually a -3 when we go to write the cosine of the angle. Okay, so these trig ratios can be negative depending on which quadrant you're in. And we haven't seen that before because we've only been dealing with right triangles that have been like kind of like a first quadrant angle. But this angle, again, the blue angle theta there is definitely bigger than 90 degrees, so different things are possible. Okay, and then finally the tangent of the angle, of course, will be the opposite over the adjacent. Okay. And if one of them's negative, it does make the entire fraction negative, right? So it's -4/3. So what I want you guys to start noticing that the sine of the angle deals with the y coordinate, and then what we're going to do, we're going to call the hypotenuse, okay, right here. We're actually going to end up calling that the radius because we're going to make a circle out of this in just a second. So you can always think of the sine as the y value over whatever the radius is. Okay, remember the radius is just the hypotenuse. Okay, the cosine will always be the x-coordinate of the point over the radius or over the hypotenuse. And then the tangent, notice we didn't even need to do Pythagorean theorem. It's really just the y-coordinate over the x-coordinate, right? Look at the point they gave us. It was -3, 4. So 4 over -3 is just y over x. We didn't need the hypotenuse. You don't need the hypotenuse for tangent. Okay, so that was just a setup. This was not technically the unit circle yet. We're going to talk about that in 1 second. But again, the big picture, kind of what we're leading towards is that there's going to be a circle that kind of goes all the way around. And if you know the coordinates of a point, sorry, that was a terrible circle. If you know the coordinates of a point, you will be able to find the sine, the cosine, and the tangent rather quickly. Back in the previous example, where the adjacent side is always the x value here, and the opposite side is always the y value. That's just the way reference triangles are always drawn. Okay, so let's get into this more important, or not important, but kind of like a bigger concept, this whole idea of the old unit circle, okay? And this is one of those things, you know how if you go back to like Algebra 1, the quadratic formula is just like a huge topic, you know, it just shows up all the time. This unit circle is kind of like that, okay? It's the trig version of quadratic formula. It's just a biggie. It does a lot for us through calculus even, and you know, beyond. It does all this cool stuff. So the idea, all it really is, so unit circle, it's like a 1 unit circle, meaning that it's just centered at the origin. Okay, so right here, this is, you know, these are the x and y axis, that's the origin. And the radius of the circle is 1. Okay, 1 unit. So what's cool about it, like we were talking about before, is that the x and y coordinates, okay, if you know the coordinates of a point, it's going to help you find the sine and cosine of the angle formed in standard position. Okay, so first off, let's go through like the borderline points. I kind of already labeled those. You'll see the points. I guess I can highlight these here. So that point, that point, that point, and that point. Okay, and again, if this is just all based on normal x, y coordinates of points, if the center of the circle is 0, 0, and if the radius of the circle equals 1 unit, right, then that point right there would just be, it's 1 unit to the right of the origin. So its coordinates are just 1, 0. Okay, up here, it's just 1 unit above the origin, so its coordinates are 0, 1. Okay, the one to the left here is negative 1, 0, and then 0, negative 1. So what that lets us do, okay, is that if we go back to what we just talked about before, the cosine of an angle is always the adjacent over the hypotenuse, right? And we talked about, we draw the reference angles. So the adjacent is always just going to be the x-coordinate of the point. And the hypotenuse, okay, here's the cool thing, the hypotenuse is always going to be the radius of the circle, okay, when it's the unit circle, is just always going to be 1. And the reason that's nice is because what is x divided by 1? It's just x. Okay, sine of any angle formed, okay, will be the opposite side length, which will be the y-coordinate of the point over 1, which is always just y. And the tangent, like we just saw, will be the opposite over the adjacent, so it'll be the y over the x. Now, let's get some numbers and see what that means, right? Okay, here's the deal. Look over here where I have this set up. Cosine of 90, sine of 90, tangent of 90, for example. Okay, what we need to do, we need to think about, all right, 90-degree angle. Where's 90 degrees? So if we think about 90 degrees, we always start here, right? 90 degrees would be straight up there. So the coordinates of the point for 90 degrees are 0, 1. Okay, the cosine of 90 degrees, the cosine is always the x-coordinate. So the cosine of 90 degrees of this point right here, the x-coordinate is 0. The sine of 90 degrees, what's the y-coordinate up there? 1. Okay, what's the tangent of 90 degrees? Tangent always equals the y over the x. 1 over 0. Okay, what's 1 divided by 0? Can you divide by 0? Nope. So the tangent of 90 is actually an undefined value. It does not exist. Okay, it's undefined. Now, what that means for us is that any old point, let's say we had some other triangle in there, you know, let's say the triangle is here, okay, and there just happen to be some random x and y coordinates of that point, the sine and cosine would just be the x, the sine would be the y coordinate, the cosine would be the x coordinate. Okay, so let's talk about how we're going to use this. Okay, here's a couple more examples. The sine and cosine of 90 we just talked about. Look at example J. Okay, they do a similar example for a 180-degree angle. So 180 degrees, we just need to know the coordinate, or the point is there, so the coordinates are negative 1, 0. Okay, and if you just always remember, the sine of the angle is the y-coordinate, because that's the opposite side length. And the cosine of the angle is the x-coordinate. Okay, that'll give you these two values right here. If I ask you for sine of 180, your process is you're going to think, all right, where's 180 on the unit circle? There's 180 degrees. I know it's 1 unit to the left of the origin, so the coordinates are negative 1, 0. So I know that the sine is the y value and the cosine is the x value. Okay, and that works anywhere. Okay, so let's start doing some work here. Let's think about, we had all these special angles, right? We had these 30s, these 45s, and these 60s, okay? And I had you guys a while back, we drew the special right triangles, and we labeled all the side lengths, and we kind of knew those values exact. Okay, here's the best part. The unit circle, let me give you a, okay, so in quadrant 1, okay, just some notes. We already knew the coordinates of the 0-degree angle and the 90-degree angle, okay? And let me just put off on the side here. We know that the x is always the cosine of the angle. The y value is the sine of the angle. Because again, if you think about that, just to visualize one more, for example, look at this red triangle right here, right? Boom, boom, boom. Okay, whatever this angle is, okay, the x-axis right here is the adjacent side to that angle. Okay, so there's some x-coordinate here. The y-coordinate of the point is that distance, okay, which is the opposite side length to our angle theta. And the whole thing that makes this work again is that the hypotenuse is 1, okay, because we are on the unit circle. Okay, so we kind of talked about that. So let's get some specific values in here and get this pattern going, okay? But that's the whole idea. So these three angles, okay, the red one, the green one, and the white one, right? Okay, they are the three special angles that we studied earlier. They are your 30-degree. This red one is a 30-degree angle. Okay, the green one, from there to there is 45 degrees. And the white one, I'm not going to draw it, but it's 60 degrees. Okay, and what we're going to do, we are going to put a pattern together to get these ordered pairs for the 3 points that we see. Okay, once we know those, we will then know the sine and cosine of the angles, because again, the x-coordinate is just the cosine of the angle, the y-coordinate is the sine of the angle. So here's this pattern, okay? Every single one of these has a 2 in the denominator. Every single one has a 2 in the denominator, unless it's a 0 or 90-degree angle or the 180 or 270. If it's in the middle of a quadrant like these, it's going to have a 2 in the denominator. Okay, here's the cool trick. So if you think about when we start, let's get a nice little color here. Okay, when we start here, the y-coordinate is 0, right? As we move our way up, think about what happens to y-coordinates as you go higher on a graph. They get bigger, right? So here's the deal. It goes 1 over 2. I'm just changing the y-coordinates. The square root of 2 over 2 and the square root of 3 over 2. Okay? X-coordinates now. Think about x-coordinates. Right here, the x-coordinate is 0, right? Because you're on the y-axis. As you move to the right on a graph, the x-coordinates get bigger in that same pattern. 1, root 2, root 3. Okay, what we just did, check this out. We just put the cosine and the sine of all of those angles. Okay, for example, the cosine of 30 degrees and the sine of 30 degrees. Cosine is the x-coordinate. Okay, this point is the 30-degree point. The cosine is root 3 over 2. The y-coordinate is the sine of 30, which is 1/2. Okay, what about for the 45? 45 is the easy one because both values are the same. The sine of 45 degrees and the cosine of 45 degrees. This green one here is the 45-degree angle, right? It's the middle. It goes 30, 45, 60. There's the cosine of 45. There's the sine of 45. They are both root 2 over 2. Okay, 60 degrees. Cosine 60, the sine of 60. Okay, 60 degrees, all you need to know, 60 degrees, the tallest angle, right? Cosine's the x-coordinate of that point. Sine is the y-coordinate of that point. Okay, boom, we know them all. That's it. Okay, you know those values. Watch what we can do when we start moving to different quadrants. Preview here is talk about that. Okay, when we move to the second quadrant, let's say, for example, we have an angle that has a terminal side in the second quadrant. Okay, it's the same three reference angles. That first one up is a reference of 30 degrees. The middle one in a coordinate is always a 45-degree reference angle. And the tallest one is always a 60-degree reference angle. So the actual angle, okay, well, let's get coordinates and then we'll talk actual angles. So the coordinates follow the exact same pattern again. Okay, every single one of them has a 2. They're all over 2. Over 2, over 2. And we do the same thing. For the, let's do the y values first. If, let's say we start when the y value is right here, the y value is 0, right? As we move up, the y values go up. Root 1, root 2, root 3. Okay. Here's where the x coordinate is 0. As we go that way, as you go to the left, what happens to the x values? Okay, they're negative, right? But they're still -1, then it's getting more negative and more negative. So it's always this pattern of 1, then root 2, then root 3. It's just they happen to be negative in the second quadrant. Okay, what that means for us is this. Let's say I ask you guys, or you see a problem that says, what is the sine of 150 degrees? Okay, and everyone's first instinct is, I'm going to type it in a calculator and get some decimal. Okay, and then whatever, that's fine. Not what we want here, though. Okay, we need an exact value. Here's how I know we can do it exact. Okay, where is 150 degrees? Okay, well, 150 degree angle, let me just do a little sketch inside of a sketch. 150 degree angle starts here, and it goes around there. 150 degrees would be right there, right? We need to think about its reference angle, okay? Reference angle, how far away are you from the x-axis? How far are we from 180? We're 30 degrees away, right? Okay, so what we do is we say, all right, I know it's a 30-degree reference angle, so I'm going to use these coordinates. That's the 150-degree angle. Okay, it's 30 degrees short of 180. So we say, all right, what's the sine is the y-coordinate. What's the y-coordinate there? +1/2. Boom, we're done. That's the sine of 150. Okay, I'll try one more. Let's say, what if I ask you, what's the what's the cosine of, I don't know, 135 degrees? Okay, you're going to say, all right, 135 degrees, no big deal, right? I can draw a 135-degree angle. Now it starts there. It's between 90 and 180. How far short of 180 was it? How much away from 180? From there to there. 180 minus 135 is a 45-degree reference, right? Reference angle is 45 degrees. Okay, so I'm going to say, all right, here's my 135-degree angle. What is the x-coordinate there? Because I need the cosine, and the cosine is the adjacent side, right? X value. X value is -√2 over 2. Okay, that's what this can do for you. Okay, these patterns continue. This is like kind of the whole thing. Okay, ton of information on there. It looks super overwhelming, but I'm here to show you there are really some nice patterns. And honestly, if you can just really own the first quadrant, okay, if you can get that part down, and I'm going to show you the easy way to do this. Okay, you don't really have to do any calculations or anything. If you can count, basically, you're going to be able to fill this out. If you can get the first quadrant done, all those patterns will apply to the other quadrants, and it will help you answer these questions quickly. Okay, so let's get into it. Throughout the entire unit circle, okay? You can find these printed out online. This is not some secret. Sometimes you may have to fill out a quadrant on a test or something. But again, just go online if you want to print one out just to help you see some patterns. But again, let's start taking a look and noticing the patterns I was showing you. Again, how the y values go from 0, they go up to 1/2, up to √2 over 2, up to √3 over 2. The very top, we know the coordinate is 1. Okay. Back over here at 180 degrees, y-coordinate 0, and they work their way back up again. Okay. The unit circle can be organized kind of however you want it. Usually, the coordinates obviously go on the outside there. And then you can see if you have a third or fourth quadrant angle, the patterns still continue, right? These y values, again, if 0 is there, as you move your way down, they're going negative, negative 1 over 2, negative root 2 over 2, negative root 3 over 2, and then you finally get to the bottom y value of negative 1, and then it just works its way back up. So just spend a little time with this. I'm going to do a couple more examples in this video, but it's just a way kind of to organize things, okay? And my whole point really, though, is if you know, like I said, if you can own this whole first quadrant, then and know the patterns and know how to get the x and y coordinates, you could then apply it to anything. So like if you have a problem dealing with, let's say, a 315 degree angle, let's say your angle ends up down here, right? Okay, you can just ask yourself, all right, 315 is how far away from the x-axis? It's 45 short, right? So you should notice the 45 degree coordinates and the 315 like really match up. The only difference, right? The only difference is that the y coordinate down here is a negative number, because in the first quadrant everything's positive, but they're still all root 2 over 2s. It's still a 45 degree reference angle, right? It's still matching up with the 45 degrees. So let's do a couple quick examples and kind of put this together. So let's say we want the sine and the cosine of a 300 degree angle. Okay, my advice, let's get a quick little sketch so we can figure out what the reference angle is going to be. Okay, so 300 degrees, if every angle starts there, I know 300 is going to be down in the fourth quadrant. I know that it's 60 degrees short of a full circle, so that's 300 degrees. Okay, so I can see the reference angle, right? The reference angle from the terminal side back to the x-axis is 60 degrees. So what we need to think about, okay, and let's just draw that entire first quadrant. Okay, I need to know the sine and cosine of a 60 degree angle, and that will tell me what the values for 300 are, okay? Because again, the sine is just the y coordinate and the cosine is the x. So let's draw all three. So there's only three angles we need to know, right? 30 degrees, 45 degrees, and then the one for this problem is 60 degrees. Okay, and let's get those coordinates, and you can use those over and over and over to solve any one of these problems. Okay, it seems like a lot, but again, all these numbers just repeat themselves. Okay, and then of course there's 0 and 90. So the 0 degrees is the full x value, 1, 0. 90 degrees is 0, 1. And then it's just that counting trick where, again, everything has a 2 in the denominator. Okay, and we just kind of count our way up, right? I usually do the y values first for whatever reason, so the y's go up from 1 to root 2 to root 3. Those are the signs. And the x's start at 0 here, and as x values get bigger as you move to the right on the graph, so they go from 1 to root 2 to root 3. Okay, so if you can just, if you have problems like that, if you just sketch that little figure, it takes 30 seconds, use that for every single one of these. Because all we need to do now, 300 degrees, I know 300 degrees is going to map up with the 60 degree reference angle, right? So I'm using those values. So the sine of 300 degrees and the cosine of 300 degrees are just the same as they are for the 60 degree angle, except the only difference, okay, remember the 300 degree angle is actually down in quadrant 4, right? So down there, y coordinates are actually negative. So the sine is the y value, but we need to make it negative. That's the one thing you got to watch for, okay? But in quadrant 4, the x coordinate is still positive, and we know its value needs to be 1/2. Okay, let's set up the 225, okay? So let's say, actually negative 225, right? Negative 225. Let's just draw that angle. Negative 225. Theta equals negative 225. Okay, so negative just means go the other way. Okay, we're still starting here always, but instead of going up through quadrant 1, I'm going to go this way. So there's negative 90, there's negative 180. I need to go to there. Okay, so the question is, how far past 180 did I go? Because the reference triangle is going to be this, the reference angle, right? And we said we went negative 225, so we did the negative 180 plus, we did 45 more, right? I did 45 past 180 in the negative direction to get to 225. So I'm going to use a 45-degree reference angle, which is this guy here, right, where they're both root 2 over 2. So the cosine of negative 225 and the sine of negative 225. I know they're both going to be root 2 over 2. We just got to ask ourselves, is it negative or positive or one of each or whatever? So if you think about a point on that terminal side, it's in quadrant 2. The x value is negative. Okay, so the cosine will be negative root 2 over 2. Okay, but on that point, the y value, think the opposite side, the y coordinate is still positive root 2 over 2. Okay, so that's kind of how that works. It does take a little time, okay, but if you can really organize the first quadrant and you know how to find the reference angles, you should be able to answer these. Now, for whatever reason, like a lot of people kind of draw a blank when these show up. I just remember getting tests and people will either leave some of these blank or they will just type it into a calculator and give me a decimal or something. And really, we need to know these values exact. These really could be like no calculator problems because the exact values show up, and we're going to do some other things with them. And you know, pre-calc and beyond, and calc, you just really have to know them. Okay, and it just takes time. So put some time in and practice when you can. Okay, and lastly, I'm not going to do this example right now. I can certainly do more later. But the third part, which was 5 pi over 6, just convert that to degrees, and then you can kind of do the same process. Okay, last thing I want to cover, how do we get the tangent of any of these angles? And basically, if you know the sine and the cosine, which we just spent some examples, you can use those to get the tangent. So let's walk through an example. So let's think about the tangent of 45 degrees. Okay, so, you know, we did this before, actually. We did this with the triangle, with the x root 2, all that stuff. But to do it with the unit circle, what you need to know is that tangent, of course, is opposite over adjacent. So if we think about the three angles, right, 45 degrees is the middle one. So it's the one where they're both root 2 over 2's. Okay, so if tangent is opposite over adjacent, in terms of the unit circle, that is just the y value over the x value. Okay, right? Because if you picture that triangle here, right, the opposite, like we always said, is always the y value, and the adjacent is always the x value. So tangent will always just be the y over the x. Okay, so in this case, the tangent of 45, it's the y coordinate over the x coordinate. So, you know, hopefully you can see what's going to happen, but just to see it drawn out, it's root 2 over root 2 divided by root 2 over 2. It's something divided by itself, right? So the tangent is 1. Let's do one where that's not the case, where we actually have to do a little math. Let's say it's we want the tangent of 120 degrees, okay? So 120 degrees, okay? That means the reference angle, right, the reference triangle for 120 is this guy right here, right? Okay, what is the reference angle there? Okay, how far from 180 were we is the question, right? Reference angles get back to 180 if you're in quadrant 2. So we should hopefully recognize that it's a 60-degree reference angle. Okay, that means that we can find the coordinates using the pattern here. There's the 30-degree reference, there's the 45. We're at the big one, the 60, right? So what are the coordinates of the big one? Okay, let's think about that. We know the coordinates. Oops, let me get the pen back on there. The coordinates up here, the y values are going up 1 to root 3 over 2. Okay. And remember the x coordinates as we go to the left are going negative, and this is the first one, so it's negative root 1 over 2. Okay, just to show the rest real quick, it'd be negative root 2 over 2, and positive root 2 over 2. And then this would be the 1/2 negative root 3 over 2. Okay, but the one we're using up here, right, 60-degree reference angle. And since we need the tangent, we need to take the y value divided by the x value. So it just ends up being a fraction divided by a fraction. Okay, so we're going to take the y value of root 3 over 2 divided by the x value, which is negative 1/2. How do you divide by a fraction? Multiply by a reciprocal. All right. Okay, so to do that, the 2's do cancel out. It becomes root 3 over negative 1. And something divided by negative 1, of course, just makes it negative. So our tangent there is going to be negative root 3. Okay, so we'll do some more practice, like I said, but that's really the idea. If you use the y value and the x value, it can also be thought of as it's just the sine over the cosine. The tangent does equal sine over cosine. That's actually an identity that we'll talk about as well. All right, so again, a lot of new stuff. Put some time in. We'll spend some time practicing, and please send me questions. All right.